CCIE-level scenario-based STP troubleshooting Q&A. Portfast and BPDU Guard scenarios. Portfast receiving BPDU. Scenario: you configured Portfast on an access port, but it receives a BPDU. What happens? Answer: if BPDU Guard is enabled, the port will go into air-disabled state. Without BPDU Guard, the port loses Portfast behavior and starts participating in STP. Portfast with hub risk. Scenario: a port with Portfast configured connects to a hub. What's the risk? Answer: if another switch is later connected via the hub, it may create a loop because the port transitions immediately to forwarding. Portfast on trunk. Scenario: you configured spanning tree Portfast trunk on a trunk port. Why would you do this? Answer: used for trunks towards end devices like servers or hypervisors that require immediate forwarding, e.g., VMware NIC teaming. Not recommended between switches. Guard mechanisms. Root guard. Scenario: a port configured with root guard receives a superior BPDU. What happens? Answer: the port transitions to root inconsistent state, blocked. Once superior BPDUs stop, the port automatically recovers. Loop guard. Scenario: a unidirectional fiber link causes one switch to stop receiving BPDUs. What happens if loop guard is enabled? Answer: the port remains in loop inconsistent, blocking state instead of transitioning to forwarding, preventing a loop. BPDU filter and inconsistent states. BPDU filter risk. Scenario: a port configured with BPDU filter is connected to another switch. What happens? Answer: the port will suppress BPDU transmission, so the other switch may think it is the root. This can cause a loop if not carefully managed. BPDU filter is risky in production. Inconsistent port state. Scenario: a switch is showing inconsistent port state in STP. What could be the reason? Answer: this happens when root guard or loop guard is triggered. It means the port is blocked due to receiving unexpected or missing BPDUs. BPDU filter is one of the most dangerous STP features if misconfigured, as it can easily create bridging loops. Root bridge election. Equal priority. Scenario: two switches are configured with bridge priority equals 0. Who becomes root bridge? Answer: the switch with the lowest MAC address wins the root bridge election. Root bridge failure. Scenario: a root bridge fails. How is the new root bridge selected? Answer: the remaining switches run the root election process again. The switch with the next lowest bridge ID, priority plus MAC, becomes root. Primary versus secondary. Scenario: what happens if a switch is configured as spanning tree root primary and another as spanning tree root secondary? Answer: Cisco automatically lowers the priority of the primary to 24576 and secondary to 28672, ensuring predictable root bridge election. STP load balancing and unexpected behavior. Load balancing with multiple VLANs. Scenario: a network has multiple VLANs. STP load balancing is required. How do you achieve it? Answer: configure per VLAN root bridge priority so that one switch is root for some VLANs and another switch is root for other VLANs. PVST+/RPVST+ allows this. Higher priority not becoming root. Scenario: a switch in the network has a higher priority but does not become root.
Why?
Answer: it might be receiving superior BPDUs from another switch with lower bridge ID on its root port, so it cannot win root election. MST and interoperability. MST mapping mismatch. Scenario: in MST, one switch has a different VLAN to instance mapping. What happens? Answer: the switch forms an MST region boundary, and CST, common spanning tree, is used between them, potentially causing suboptimal paths. MST with RSTP. Scenario: you enable MST, but RSTP is running on another switch. What happens? Answer: MST switches communicate with RSTP switches using CST, instance 0, BPDUs. Interoperability works but may cause slower convergence. Physical loops and ether channel. Self-BPDU reception. Scenario: a switch receives its own BPDU on a port. What does that indicate? Answer: it usually indicates a physical loop, cable mismatch, or bridging loop. STP should block one port, but troubleshooting is required to fix cabling. Ether channel and STP. Scenario: an Ether channel bundle has 4 links. How does STP treat it? Answer: STP treats the Ether channel as one logical port. If one physical link fails, STP does not reconverge. Traffic is redistributed across remaining links. Convergence and troubleshooting. RSTP root port failure. Scenario: a root port fails on a switch. How does RSTP handle it? Answer: RSTP immediately promotes an alternate port, if available, to root port, allowing sub-second convergence. Continuous TCN BPDUs. Scenario: you notice constant TCN BPDUs in your network. What does it mean? Answer: a port is flapping between up/down or forwarding/learning, causing continuous topology changes. This can flood the network with MAC address flushes. Port stuck in listening. Scenario: a port is stuck in listening state for too long. What could be the cause? Answer: STP timers may have been misconfigured, forward delay too high, or the port is continuously receiving superior BPDUs. Critical STP issues. MAC address table instability. Scenario: you see MAC address table instability and high CPU on switches. What's the likely issue? Answer: a spanning tree loop is present, possibly due to disabled STP, misconfigured BPDU filter, or unidirectional link. This is one of the most critical STP issues to identify quickly, as spanning tree loops can bring down an entire network within seconds. Always check for disabled STP on any switches, misconfigured BPDU filter settings, unidirectional links, especially with fiber, incorrect port-fast configuration on interswitch links. Immediate action is required to isolate the affected segment before the entire network becomes unusable due to broadcast storms.